Before anything else, an acknowledgement. If I have seen further, it is by standing on the shoulders of giants. Everything in this talk rests on the work of researchers and writers who came before. In particular, a thank you to Chip Huyen for taking the time to write AI Engineering, one of the books this explainer draws from. Let's get into it. A quick word on who's talking. I'm Aaron Clark, Crypto Jones Online. I'm a graduate student at Eastern University, and I spend my time where security meets machine learning. You can find me on GitHub as Crypto Jones or reach me on Mastodon. With that, let's get into LoRa. Building LoRa adapters for frontier models. By the end of this, you'll understand what a LoRa adapter is, the small piece of math that makes it work, the handful of knobs you actually tune, and how to train, merge, and serve one. No giant GPU cluster required. Start with the pain. Say you want to fine-tune a 7 billion parameter model. In half precision, the weights alone are about 14 gigabytes. Training also needs gradients, another 14, and the Atom Optimizer keeps 2 extra values per parameter in 32-bit. That's roughly 56 gigabytes. Add it up, and you're north of 80 gigabytes of GPU memory before your dataset even shows up. That's data center hardware. A normal 24 gig graphics card cannot do it. So the question becomes, can we adapt the model without touching all of those weights? Here's the trick. Instead of nudging billions of weights, we freeze them completely. The base model does not change at all. Then we bolt a tiny trainable patch onto the layers we care about and train only that. We're talking a fraction of 1% of the parameters. Why on earth would that be enough? Because researchers found that the change a model needs to learn a new task has, in their words, a low intrinsic dimension. The update lives in a small subspace, so a small patch can capture it. That patch is a LoRa, low-rank adaptation, from a 2021 paper by Hu and colleagues at Microsoft. Let's make it concrete with one line of math. Every layer has a weight matrix, call it W. Fine-tuning learns an update to it, delta W, and the new weights are simply W plus delta W. In LoRa, W is frozen, so every bit of learning lives inside delta W. That reframes the whole problem into one question: how do we represent and train delta W without paying for a full matrix the size of W? Here's the heart of LoRa. Instead of storing delta W as one big matrix, we factor it into 2 skinny ones. Delta W is approximately B times A. A is short and wide, B is tall and thin, and they meet in the middle at a small number called the rank R. The product BA has exactly the same shape as delta W, but you only ever train A and B. Put numbers on it. Take a square weight matrix like GPT-3's, 12,288 on a side. That's about 151 million parameters. With rank 8, A and B together are about 197,000 parameters. That's roughly 768 times fewer trainable numbers for that one matrix. Multiply across the model and the savings are enormous. Why is that legal? Look at the shapes. A tall, thin matrix times a short, wide matrix gives you back something the full size of delta W. But the result can only point in R-independent directions, R being that small rank. You're deliberately constraining the update to a low-rank subspace. The bet LoRa makes, and it pays off in practice, is that a single task only needs a handful of directions of change. So a couple of skinny matrices are genuinely enough. Here's how the patch plugs in at runtime. For an input X, the layer output H is the original frozen layer, WX plus the LoRa patch, BAX, scaled by alpha over R. Alpha is just a fixed dial for how loud the patch is. 2 clever defaults make this stable. We initialize A with small random noise, and we initialize B to all zeros. Multiply them, and at the very first step, the patch is exactly 0, so the model is byte for byte, the original pre-trained network. Training then nudges B away from 0, so you always start from the known good model, and only drift as far as the task requires. No random shock to the weights. There are really only four knobs. Rank R is the capacity of the patch. 8 to 64 is the usual range. Bigger is more expressive but costs more parameters. Alpha is the scale. A common rule is to set alpha roughly equal to R or twice R and then stop fiddling. Dropout inside the patch, around 5 to 10%, fights overfitting on small data sets. And target modules decides which layers get a patch. Classically, the attention query, key, value, and output projections. And these days, the MLP layers too. More targets and higher rank cost more, but usually help. That's it, those four. Training is refreshingly boring, which is the point. Step 1, freeze every base parameter. Step 2, insert the LoRa A and B matrices into your target layers. Those become the only trainable tensors. Step 3, train with a completely ordinary optimizer like Atom W and your ordinary loss. No exotic schedule. Concretely, in Sebastian Raschke's worked example on a 124 million parameter GPT-2 at rank 16, the trainable count drops from 124 million to about 2.7 million, roughly 2%. And because the optimizer only tracks those 2.7 million, its memory shrinks too. That's where the real RAM savings come from. LoRa shrank the training cost, but the frozen base model is still sitting in memory at full size. QLoRa attacks that. First, it stores the frozen weights in just 4 bits each, using a format called NF4 that's shaped for the bell curve distribution of neural network weights. Second, double quantization compresses even the little constants used by the quantizer. Third, paged optimizers let optimizer memory spill to CPU RAM during spikes instead of crashing. The LoRa patches themselves stay in full 16-bit precision and do all the learning, with gradients flowing back through the frozen 4-bit base. The headline result from the QLoRa paper: you can fine-tune a 65 billion parameter model on a single 48 gigabyte GPU. That's the democratization moment. Let's see it in code. 3 small libraries do the heavy lifting: Hugging Face Transformers, PEFT, and Bits and Bytes. First, we load the base model in 4-bit. We build a bits and bytes config that says, load in 4-bit, use the NF4 quant type, compute in float 16, and turn on double quantization. Then we load the model, here an 8 billion llama, passing that config and letting it place itself on the GPU. That one config object is the entire quantization half of QLoRa. Now the LoRa half. We call prepare model for k-bit training, which does some bookkeeping so gradients behave with a quantized base. Then we describe the adapter with a LoRa config, rank 16, alpha 32, a little dropout, no bias adaptation. It's a causal language model. And we target the attention projections: query, key, value, output. One call to get PEFT model wraps the frozen base with those trainable patches. Print the trainable parameters, and you'll see something like 0.1% to 1% of the model. Everything else is frozen. Finally, training looks like any other Hugging Face job. Set up training arguments: epochs, batch size, gradient accumulation to fake a bigger batch, a learning rate around 2 times 10 to the -4, mixed precision on. Hand the model, args, and dataset to a trainer and call train. When it's done, save pre-trained writes out only the adapter, just the A and B matrices, a few megabytes. The multi-gigabyte base model never changed, so you never have to copy it. That asymmetry is what makes LoRa so practical to store and share. Once trained, you serve a LoRa one of 2 ways. Option 1, merge. You fold the patch permanently back into the weights. W becomes W plus the scaled BA, and now you have a normal model with 0 extra inference latency. That's ideal when you've got one fixed task. Option 2, keep them separate and swap. You hold a single frozen base in memory and a library of tiny adapters on disk, then hot swap the right one per request or per customer. One base model can be your support bot, then a named entity extractor, then a CQL writer, just by changing which few megabyte adapter is loaded. The cost is a small per call overhead. Merge for speed, swap for flexibility. Here's the whole trade-off on one slide. Full fine-tuning trains 100% of the weights in 16-bit and needs something like 84 gigabytes for a 7B model. Every saved model is a full copy. LoRa trains a fraction of a percent, keeps the base in 16-bit, fits in the high teens of gigabytes, and saves adapters that are mere megabytes. LoRa pushes the base down to 4-bit and gets you into single-digit to low teens gigabytes, a 7B on a normal gaming GPU. And critically, on most tasks, both LoRa and QLoRa come within a hair of full fine-tuning quality. You give up almost nothing and save almost everything. If you want to go build one this week, here's the recipe. 1. Pick a base model and load it in 4-bit for QLoRa or 16-bit for plain LoRa. 2. Start with rank 16, alpha 32, 5% dropout, and target the attention layers, adding the MLP if you have room. 3. Format your data to the model's chat or instruction template. This matters more than people expect. 4. Train a few epochs with Atom W and a learning rate around 1 to 2 times 10 to the minus 4. 5. Evaluate on data the model never saw and only raise the rank if it's clearly underfitting. 6. Merge for a single task, or keep and swap for many. That's a real workflow. A few traps to dodge. If quality plateaus, your rank is probably too low, raise R before you blame the dataset. Targeting only attention can leave performance behind. Add the MLP layers. LoRa generally wants a higher learning rate than full fine-tuning, so don't go too timid. The single most common silent failure is the wrong chat template. If your formatting doesn't match what the base expects, you get garbage. When merging, remember a QLoRa adapter should be merged into a 16-bit copy of the base, not the 4-bit one, or you lose precision. And if your loss never moves at all, check that the adapter is actually attached. Remember, B starts at 0, so a miswired adapter looks exactly like no training. Let's tie it together. Full fine-tuning is too big, mostly because of the optimizer state. So we freeze the base and learn only the update delta W. We factor that update into 2 skinny matrices, B times A at a low rank, a fraction of a percent of the parameters. At runtime, the layer is WX plus the scaled patch, and because A is random and B is 0, you always start from the original model. QLoRa quantizes the frozen base to 4-bit, so even frontier scale models fit on a single GPU. And you ship by merging for speed or keeping adapters separate and swapping for flexibility. That's the whole mental map. Everything here stands on the shoulders of these: the original LoRa paper by Hu and colleagues, the QLoRa paper by Detmers and colleagues, Chip Huyen's AI engineering, Sebastian Raschke's build a large language model from scratch, and Alamar and Grutendorst's hands-on large language models, all of which explain this beautifully. The intrinsic dimensionality paper that justifies why low rank works, and the Hugging Face PEFT docs for the code. Go read them. And that's the payoff. A frontier model, fine-tuned on a single GPU, with a patch you can email to a colleague. 2 years ago, that sentence was science fiction. Now it's a weekend project, so go build one. Thanks for watching. Crypto Jones, Ronin 48.